Let's consider this example next. Adding up n goes from 1 to infinity. I'm going to make it be -1 to the n plus 1 over n. I will write this out with the plus dot dot dots. When n is 1, it's -1 squared over 1. When n is 2, it's -1 cubed over 2. When n is 3, it's -1 to the 4th over 3, then -1 to the 5th over 4, etc. If you simplify this, you get 1 minus a half plus a third minus a fourth plus a fifth minus a sixth, etc. That should look kind of familiar. If all those were plus signs, we even have a name for it. What was it called? It was called the harmonic series. But yeah, you're right, Daniel. This is called the alternating harmonic series. What about the harmonic series did I say you should know for the rest of your life? It diverges. The harmonic series, which is a p series with p equal to 1, diverges. We use the integral test to confirm that, because the integral of 1 over x gives you natural log of x, and natural log of x goes to infinity as x goes to infinity. That was something we talked about a week ago. The harmonic series diverges. What about the alternating harmonic series? Before I just tell you the answer, let's see if we can get some intuition at the same time reinforce a key idea that many people don't understand. The terms of a series are not the same as the series itself. The ANs converging doesn't mean the series converges. If the ANs converge to 0, the series might or might not converge. Whether the series converges or not is completely dependent on whether the sequence of partial sums converges or not. To be consistent with the book's notation in this context, I'm actually not going to call that AN. I'm going to call it BN. I am going to think of it as -1 to the n plus 1 times 1 over n, and call 1 over n AN. So this is different. This is a different use of the notation AN to be consistent with the book's form of what's called the alternating series test. So the first partial sum, S1, the things you're adding here are really the b's. It's B1. B1 is 1. Not much to do there. What's the second partial sum? It's B1 plus B2, which by this notation really is A1 minus A2, because when n is 2, -1 to the third power is -1. That's why I get a minus sign there. So this is 1 minus a half, which is a half, 0.5. When n is 3, the third partial sum is B1 plus B2 plus B3, which, in terms of the A's, is A1 minus A2 plus A3. You can also just look at the series itself. That's 1 minus a half plus a third. What does that equal? Get a common denominator of 6. It's 6 minus 3 plus 2 all over 6, 5/6, or 0.83 with a 3 repeating. Let's do one more by hand. S4 is B1 plus B2 plus B3 plus B4. The B's are the terms that are being added. In terms of the A's, it's A1 minus A2 plus A3 minus A4. For our particular alternating harmonic series, that's 1 minus a half plus a third minus a fourth. Now get a common denominator of 24. It's 24 minus 12 plus 8 minus 6 all over 24. 14/24, which is 7/12, which is 0.583 with the 3 repeating, etc. Let's continue now, but with a calculator. First, I'll just confirm that fourth partial sum S4. 1 minus a half plus a third minus a fourth. Yep, 0.583 with a 3 repeating. Now let's add a fifth. According to the calculator, S5 is 0.783 with the 3 repeating. Now subtract a sixth. S6 is 0.616 with the 6 repeating. Add a seventh. S7 is, I'll just approximate now, 0.7595. Keep going. Now subtract 1/8. S8 is about 0.6345. Couple more, add a ninth. S9 is about 0.7456. And finally, S10, I'll subtract a tenth from that, 0.1. S10 is about 0.6456, etc. Do these have a limit as n goes to infinity? It should feel like maybe they do. On a number line, if I graph them, S1 is 1, S2 is 0.5, S3 is 0.83 with a 3 repeating, maybe right about there. S4, that was 7/12, 0.583. There's S4, about, well, okay, 0.583 with the 3 repeating. S5, I'll just draw them now without writing the numbers. 0.783, it's about there. S6, maybe right about there. S7, S8, S9. Oops, that's supposed to be S9. And S10, maybe right about there. These partial sums form a sequence. Jumps back and forth, but they're getting closer and closer together. Do they approach a limit? It's not a proof, but I'll just say they do. To some limit right there, call it S. The limit of the SNs does exist. It can be proved, and we're about to prove it with the alternating series test. That is the sum of the BNs, which is the sum with our notation from the ANs in this example of -1 to the n plus 1 times AN, where AN is 1 over n. Technically, to prove this, we need to apply something called the alternating series test. You need to realize with the alternating series test, there's conditions to be able to use it, hypotheses that are necessary. One thing that's necessary is that the A's, being 1 over n in this case, are positive numbers that go to 0, that decrease to 0, I should say. You'll see in the book, so the ANs are 1 over n here. They are always positive and they decrease. AN plus 1 is less than AN. And not only did they decrease, but they decrease to 0. That's definitely true here. 1 over n satisfies these properties. That's part of the hypotheses of the alternating series test. Therefore, you can say by the alternating series test, this series converges. The alternating series test happens to use an n minus 1 power, but it's not a big deal. -1 to the n minus 1 power equals -1 to the n plus 1 power when n is an integer. That's fine. Okay, so this exists by the alternating series test. The series does converge. Alternating series test. However, it doesn't tell you what it converges to. Let's explore that a little bit with more technology. There's another theorem that I do want you to know called the alternating series test error-bound theorem for a series of the form n goes from 1 to infinity of, again, the book uses an n minus 1 power here, but it would also be fine to use a n plus 1 power. For an alternating series like this, where the A's form a decreasing positive sequence that converges to 0, the absolute value of S minus Sn is less than An plus 1. And this absolute value of S minus Sn represents the distance between S and Sn on a number line. And you could say it's the error, the absolute error. Absolute error in using Sn to approximate S. This theorem says that's got to be less than An plus 1, for sure, guaranteed. Not going to prove this, but let's use it to, for example, figure out how big n should be to guarantee that Sn, or nth partial sum for the alternating harmonic series, it's within, say, 0.001 of S. For the alternating harmonic series, how big should n be to guarantee, emphasis on the word guarantee, that the error, the absolute error, is less than 0.001 10 to the negative 3, which is 1 over 1,000. It's a guarantee. The theorem gives you a guarantee. It's possible. It's possible you might be able to get away with a smaller value then. For the alternating harmonic series, what is An plus 1? That comes from the theorem. It is 1 over n plus 1. I want that to be less than 1 over 1,000. How big should n be? Solve the inequality for n. Take the reciprocal of both sides. Careful though, that switches the direction of the inequality around. You take the reciprocal of both sides, you're effectively plugging both sides into the function of 1 over x, whose graph is decreasing. And because of that, the inequality switches direction. It makes intuitive sense too. If you want 1 over n plus 1 to be small, n plus 1 itself better be big. That's equivalent to subtract 1 from both sides, n being bigger than 999, like 1,000 or more. So if we use n equal to 1,000 or more, we are guaranteed to be within 0.001 of the true answer. Let me go ahead and confirm this. Here is the nth partial sum. I'm using k as the index of summation here because n is going to be my upper limit of the summation sign. That's Sn. What, for example, is S of 1,000? If I enter this as it's going to be a humongous fraction. I better approximate it. 0.692647. What is the infinite series equal to? What does it sum to? It is convergent by the alternating series test. What is its sum? What is S? It's about 0.693147. Actual value, approximately, minus this approximation from a partial sum, guaranteed to be less than 0.001, and it is. It's about half as big, 0.0005. So we actually could get away with a smaller value than maybe even n equals 500 instead of 1,000. But the theorem is a guarantee. We want a guarantee. What is the number? What is this number? 0.693147. Maybe you've seen that in the calculator before. It's actually a somewhat famous number. It's actually ln of 2. This series turns out to converge the alternating harmonic series to the natural log of 2 of all things. It's true. It converges to ln of 2 exactly. If you take 2 and raise it to that power, excuse me, take e and raise it to that power, you'll get 2. Crazily enough. You could write that as an equation. I could write an e here, make that my exponent, I'd say it equals 2. An example of a crazy equation you could prove. Can we prove it? Not now. Can we prove it next week? Sort of. We won't fully prove that it converges to natural log of 2, but we will see evidence that indicates it probably equals natural log of 2 when we talk about Taylor series in chapter 10.